this particular equation is the first part. All the other part is undesired. Therefore, we will model R1 and R2 in such a case that it eliminates the channel interference, or rather it eliminates the channel effects at user 1 after the first and the second round. So we essentially set all this part to 0, and this is how we do it. Looking at user 2, the total received signal at user 2, we see that the second term is the desired term at user 2. Therefore, we model R2. We have to design R1 and R2, or auxiliary signals, such that they completely eliminate the interference from the signal intended for user 2, for user 1, sorry, which is X1, as well as remove the channel interference. And therefore we set this particular, the first term plus the other terms except from the second term, we set them to be equal to 0, and this is what we did here. So using now the equations, these two equations here, we have two equations and we have two unknowns. R1 and R2 are the unknowns. We are able now to calculate our R2 and our R1. It's also important to look at, for example, the equation received by by Eve. Looking at the total equation, or the total signal received at user 3, sorry, but at Eve, the total received signal at Eve, we see that it's very, very difficult. It's extremely difficult for Eve to find a way to decode this particular signal because of the interference caused by the channel. Because for Eve, X1 and X2 are interested. Eve is interested at getting X1 and X2, which is the signal for user 1 and user 2. But it's extremely difficult for Eve to be able to decode this particular signal to cancel the interference caused by both signals on each other, as well as the interference coming from the channel and the interference coming from R1 and R2. Therefore, it's impossible for Eve to decode this particular signal. Having said that, now let's look at some performance results from the simulations. After simulating this particular model, we look at some of the particular performance results that we got in comparison to conventional systems. So this model was simulated in MATLAB, and we used multipath Rayleigh fading channel. We used a channel with channel length of 9 and a cyclic prefix of 9. Our FFT was 64, and we used a BPSK modulation. So let's first of all look at the bit error rate, and here the bit error rate of user 1, we observe the bit error rate of user 1 and user 2, and we also observe the bit error rate of single input single output utilizing dual transmission, and single input single output utilizing single transmission. And here we can clearly observe that having dual transmission is much better than having single transmission. Therefore, this particular system that we are using is much better. So here we can see that we have we can observe the BAR of user 1 and user 2, and we can see that it's even better than conventional single input single output systems. And we also observe that we have the bit error rate of user 1 trying to listen to user 2. Now this is the internal eavesdropping, which was a problem for conventional NOMA systems, because if you remember, in the first conventional NOMA systems, user 1 or the user with a good channel usually decodes the signal of the user with a bad channel. But we can observe here that in our case it's not possible. In our case, the information is completely secure, because user 1 trying to listen to information trying to listen to user 2, its BAR is completely 0, and user 2 trying to listen to information of user 1, its bit error rate is also completely 0. And for the external eavesdropper as well, where we have Eve now trying to listen to the information intended for user 1, is also completely 0, and Eve trying to listen to user 2 is also the BAR is also completely 0. Therefore, we can say that this particular proposed system is completely secure against both internal and external eavesdroppers. We now also look at the throughput, and looking at the throughput for user 1 and user 2 in comparison with the single input single output system and a conventional single input single output system utilizing dual transmission. We can observe that we have, at lower SNRs, we have a better throughput for this particular proposed system. We look at the packet error rate, and in the packet error rate performance metrics as well, we can say that we have user 1 and user 2, and we can also observe that the PAR of our internal eavesdroppers, where we have Eve listening to user 1 and Eve listening to user 2, is completely 0. In this particular figure, we are analyzing the peak to average power ratio, and this is one of this is one of the major problems which is incurred by OFDM systems. But in this particular system, which is actually a very good breakthrough in this particular technology, we observe that the peak to average power ratio of user 1 and user 2 utilizing this particular technology is actually less compared to conventional NOMA systems. Therefore, this is a very important aspect in this particular technology. We now also look at the performance metrics of this particular system in imperfect channel conditions. What we mean by imperfect channel condition is basically we are trying to simulate how the real world looks, because channel prediction or rather trying to determine the channel of a communication system is not always as accurate as we may think. So in this particular system, we are trying to simulate or trying to see how this system performs under imperfect channel characteristics. And as we can observe, basically this E is a factor which is adding the imperfect channel, which is adding more imperfectness in the channel. And as we can observe, even when we have an imperfect channel conditions, which basically simulates the real world application, we can observe that our system, our proposed technology, still performs much better compared to conventional far NOMA user and a conventional near NOMA user. And in conclusion now, we have seen that we have proposed a secure, resilient, and effective as well as a low complexity non-orthogonal multiple axis technology. We have seen that in this particular technology we have zero information leakage to both internal and external eavesdroppers. Therefore, we can conclude that we are able to provide perfect secrecy for users utilizing this particular paradigm. We have seen that this particular paradigm is made up of two transmitters and is carried out. Transmission is carried out during two transmission rounds. This is essentially to make the auxiliary signals more complex. Auxiliary signals are also used. R1 and R2 are used and are superimposed on user signals during the two rounds. Simulation results show that the system is reliable and secure with minimum complexity than conventional communication techniques, because in this particular paradigm the user simply receives the information or receive their intended data without doing any processing. We have also seen that this particular system is suitable for future and for current and future Internet of Things, as well as massive machine time communication applications. In the future, we plan to develop this model for for more than 2 users. So this is the end of this lecture. If you want more information on this particular technology, I encourage you to visit RS Open Journal and read the entire this entire journal, which will give you a more detailed analysis of this particular technology. And with that, we come to the end of this lecture. I hope it has been informative. Thank you.